Okay, hello everyone. This is going to be about the after the midterm part of the lecture that we did and application of ANSYS in solving the 2D elements. Normally, something like this beam or plate that you are going to see was going to be treated as a simple beam as a 1D object, and we use the classic formulas and things that we learned from before the midterm one. But then we started talking about triangular 2D elements and quadrilateral elements. So let's see if we can see the application of it in ANSYS and use that as an alternative way of solving the some beam problems. This way, instead of 1D, we are going to go with two-dimensional problems. So let's say you have a plate that is really thin or thickness is really small or negligible compared to the overall shape of the plate. Let's say you have a thickness of T. So you are going to treat this object as a plane stress. Let's say two type of forces are going to be applied to it. One of them is going to be distributed load, and the other one is going to be a point load, as you can see. So how can we create something like this in ANSYS Workbench? What we will do is we will go and load our ANSYS again. We will go to geometry. Well, we have geometry from the last problem again. So let's go to File, Start Over, Yes, and go with a new project. So I will go to XY plane again. I'm not going to go with determined numbers and given values. I'm just going to give it some random numbers. The goal here is just to learn how we can apply distributed load to something like a plate or point loads. So I will go to look at, so I can look at the plane perpendicularly, and I will go to our sketching. I do have lines and everything. Let's say I want to go with the plate, a simple one. So I'm just going to go with point 0 and 0 and then drag the mouse so I can make the plate, at least the 2D part of it. Then I'm going to go and generate the model. Normally, what would I do when I do have, let's say we have the project in front of us, we are going to determine what the dimensions of this length and this side will be. But then let's say again, I'm going to go with some really random lengths. So I will go and generate the model. And the next step will be to extrude the object. Remember, this is going to be a plane stress model, so the thickness is going to be really small. Instead of 20 centimeters, I'm going to go with, let's say, 2 centimeters, which is thin enough, or the thickness could be neglected compared to the overall size of the plate. So next step is to going to generate the shape, and then we have to go to the model. For the model, we have to remember, this is from the last problem again. I'm going to right click on the geometry and update the geometry from the source. By the way, all of these force, fixed support, and force through from the last problem now is going to be known with errors because the problem doesn't know what they are, as you see these question marks next to them. So I'm going to go and get rid of force 2 because we have a force and a point force. So anyways, the fixed support, remember the plate is looking like something as simple as this plate. So this is what the plate looks like. This side of it, the left side, is going to be attached to the wall, so it's going to be a fixed support. So we will go to fixed support geometry. We are going to go with this face and apply. Then we are going to have a distributed force applied to this face and a point load applied to this node. Now, let's be realistic. If we wanted to apply the load, it's not going to be applied as a distributed load to this edge, but rather a distributed load to this surface or this face. So what we would do, we will find what the total force is from this figure. Let's say we have a length of L and a distributed load of Q newtons per meter. So the total force is going to be QL. So let's say, for example, again, I'm having a length of 2 meters and a distributed load of 2,000 newtons per meter. So the total force that is going to be applied to this face, the top face of the element, that we don't see but we see in 3D in the model, is going to be 2 times 2,000 newtons or 4,000 newtons. So I'm going to go to the model, and for the force, I'm going to say, hey, let's apply the force to this face. And now the problem is, as you see, the direction of the force is not going to be as we want. So first of all, let's go with the force of, let's say, 4,000 newtons. And the direction of it has to change. Well, how can we change the direction? It has to be upwards or in the y direction, whereas right now it's pointing in the x direction. I will go and click on this trapezoid, and I see 3 planes. I have to look for the plane that is going to be perpendicular to our normal force. There you go. Again, I chose this plane as a plane that our force is going to be perpendicular to. So I'm going to go with the force in the y direction, which is going to be perpendicular to this plane, which I choose by clicking on this plane. Anyways, our distributed load is ready to be applied. By the way, I want to change it from 4,000 to minus 4,000 because it's going to be downwards. Then it's time to apply the other force. I will go to static structural, insert, force. This is going to be the second force that is going to be applied. It's going to be your point force. Again, to be realistic, it's not going to be applied to a single node, but rather to the edge of this object, as you see here. So in order to do that, we will go here, top of here, and we will choose, so force 2 is highlighted. I will go with an edge, and for the geometry, I'm going to choose this edge and apply. So this edge was applied for the place where the force, that point force is going to be applied. The vector, let's say the magnitude of it is going to be 1,000 newtons of force, and the direction of it, as you see, is in the z direction. Again, I want it to be in the y direction. Again, I will go to click on this trapezoid that we have and choose the plane that is going to be perpendicular to the force in the y direction. All right, let's see which plane it is going to be, which is this one, apply. And this is going to be the direction of the force that we are looking for. I'm going to go with minus 1,000 newtons of point load. So now we have a combination of both the fixed support, I apologize, let's see, this force, the distributed load, and this force, the point one. So let's say I'm still looking for total deformation and force reaction for our solution. Now it's time to solve the system. Let's see. All right, if I go to the reaction force, we have 5,000 newtons of force applied to the system, which is completely correct. We had a 4,000, a summation or a combination of 4,000 newtons of downwards force, which was distributed load, and a point load of 1,000 newtons. All right. So I can go and see what the total deformation is and how it looks with respect to time. As you see, if I hit the run button, we will see how it looks like. All right, this was a really simple, brief introduction to how the system works for your 2D objects. Thank you.